Electronic Control and Digital Electronics Level 4. Module 2, Session 2.1. In this session, we will cover the following subject outcome of the Level 4 curriculum. RLC circuits, subject outcome 1.3. During our studies in Levels 2 and 3, we focused our attention on how resistive components such as resistors and light bulbs behave under DC conditions. In this section, we will consider the relationship that exists among different components when connected to an alternating voltage source, AC, either in a series circuit, a parallel circuit. The three components that we will discuss are resistors, where the unit of measurement is ohms, inductors, where the unit of measurement is henries, capacitors, where the unit of measurement is farads. It is important to examine what happens to each individual component when an AC voltage is applied to it, before we can understand how they work when combined in a circuit. We call this circuit an RLC circuit. Let us first discuss resistors. Consider this circuit with a switch and a resistor. When the switch is closed, an alternating voltage causes a current to flow through the circuit. This current increases and decreases as the applied voltage increases and decreases. As the load, R, is a pure resistance, the current and voltage will both reach their maximum or peak values at exactly the same time, and they will fall through zero at exactly the same time. Since the current and voltage rise and fall simultaneously, we say they are in phase with each other. This means that there is no phase difference between the voltage and current. The phase difference is referred to as the phase angle, and in this case, the phase angle is zero. So for a purely resistive circuit, the alternating current flowing through the resistor varies in proportion to the applied voltage across it and follows the same sinusoidal pattern. The current will achieve its maximum, minimum, and zero values whenever the voltage reaches its maximum, minimum, and zero values as shown in this waveform. As the supply frequency is common to both the voltage and current, their phases will also be common, resulting in the current being in phase with the voltage. Here is a phasor diagram for a purely resistive circuit. The effect that an alternating quantity has on a resistor is no different to that of a direct current, DC, quantity. We can therefore apply expressions according to Ohm's law here. The opposition to current flow in the circuit is called resistance and is represented by the formula R equals V over I, where R is equal to the resistor value in ohms, V is equal to the applied voltage in volts, I is equal to the current flow in amperes. Let's now discuss inductors, which we also call coils. This simple circuit consists of an inductor connected across an AC voltage source. When the switch is closed, the alternating voltage causes a current to flow through the inductor and rise from zero to its maximum value. This rise or change in the current induces a magnetic field around the inductor, which in turn opposes the current flow in the circuit. Lenz's law describes what happens. The direction of an induced current is always such as to oppose the change in the circuit or the magnetic field that produces it. In a purely inductive circuit, the voltage leads the current by 90 degrees. We can also say that the current lags the voltage by 90 degrees. This effect can be represented by a phasor diagram as shown here. This opposition to current flow is called inductive reactance, XL, and is represented by the formula XL is equal to 2 pi FL, where XL equals the inductive reactance measured in ohms, F equals frequency of the alternating quantity in hertz, L equals value of the inductor in henries. We can calculate the current by using the formula IL equals VL over XL. Now let's discuss the effect of alternating current on capacitors. When we close the switch in a purely capacitive circuit, a high current starts to flow onto the plates of the capacitor. There is no initial charge on the plates. This means that the voltage across the capacitor at the instant when an AC voltage is applied is zero. The current, however, is at its maximum. When an alternating voltage is applied to the plates of a capacitor, the capacitor is charged firstly in one direction and then in the opposite direction. The polarity changes at the same rate as the AC supply voltage and frequency. In a purely capacitive circuit, the voltage lags the current by 90 degrees, or we can also say that the current leads the voltage by 90 degrees. This effect can be represented by this phasor diagram. We calculate the capacitive reactance Xc by using the following formula. Xc equals 1 over 2 pi Fc, where Xc equals the capacitive reactance measured in ohms. F equals the frequency of the alternating quantity in hertz. C equals the value of the capacitor in farads. One way to remember whether the current or voltage is lagging or leading when dealing with inductors and capacitors in an AC circuit is to use the word civil. With a capacitor, C, I comes before V, which means that the current leads and the voltage lags. With an inductor, L, V comes before I, which means that the voltage leads and the current lags. Now that we have seen how these components behave when an alternating current is applied to the circuit, we need to discuss one more concept. It is called impedance, Z. We can define impedance as the opposition that a circuit presents to a current flow when an alternating voltage is applied. Impedance is the vector sum of both resistance and reactance and is represented by the following formulas. For a series circuit, impedance is calculated using this formula. Note that we need the square of the difference between Xc and XL. So if XL is greater than Xc, it should be placed first in the equation. For a parallel circuit, we use the following formula. Now that we have seen how resistors, inductors, and capacitors behave in alternating current circuits individually, let's see what happens when we connect them all together in an RLC circuit. A series RLC circuit consists of a resistor, inductor, and capacitor connected in series and powered by an AC source with a particular frequency. When there is a combination of resistance, inductance, and capacitance in an AC circuit, the current and voltage will be between 0 degrees and 90 degrees out of phase, depending on the values of these components. A parallel RLC circuit consists of a resistor, inductor, and capacitor connected in a parallel circuit which is powered by an AC source with a particular frequency. As with a series RLC circuit, the current and voltage will be out of phase between 0 degrees and 90 degrees, depending on the values of these components. Please note the following. In a series RLC circuit, the supply voltage is equal to the phasor sum of all the voltage drops across each component. The current flowing through the circuit is the same throughout the circuit. In a parallel RLC circuit, the total current is the phasor sum of the current flow through each component. The supply voltage is the same across each component in the circuit. The concept of resonance is critical to the understanding of RLC circuits. Resonance is a condition that will occur in a series or parallel circuit when XL equals Xc. Resistance plays no part in the resonance of a circuit. The formula to calculate the resonant frequency is F equals 1 over 2 pi square root LC. But why is the resonant frequency so important? We can explain this using the example of radio signals. The antenna of a radio receiver is receiving signals from many radio, television stations, and emergency services all at the same time. Each station broadcasts at a different frequency, carrier frequency. For example, Gagazi broadcasts at 99.99 MHz FM and East Coast at 94.4 and 95 MHz FM. Each different frequency induces a signal voltage in the antenna so that at any given time there may be many different signal voltages in the same antenna. So how can we separate the signal we want from the other signals? We can separate one frequency from the rest if we can find an inductor and capacitor combination which resonates at same frequency as the one we are trying to separate. Only this frequency will encounter zero impedance and will therefore produce a large current. All other frequencies will encounter large impedances and the currents at these frequencies will be practically zero. The tuner of the receiver is a series or parallel circuit consisting of an inductor and a capacitor, which we can make resonant at different frequencies by using a variable capacitor, or today, a varicap diode, also called a varicap diode. A varicap diode selects and passes on the required frequency to the amplifier system, and you have now tuned your receiver to the required radio station or TV channel that you wanted. There are many other uses for resonance circuits. This is why it's so important to understand how they work. Band pass, low pass, high pass, and other similar circuits all use the principle of resonant circuits. Here are some practical applications for resonant circuits. Tuning circuits. Radio and television stations as well as other applications where a specific carrier frequency is needed such as emergency services use resonant circuits. Metal detectors. Every metal has its own resonant frequency. RLC circuits are used to identify such metals. Filter circuits. These circuits are used to block certain frequencies and allow others through a circuit. End of the video. We'll be right back.